It's my pleasure to introduce Arun Krishnamoorthy from Intel, who's going to talk about the thermal challenges during tests of high-performance CPUs for client and server segments. Arun is a senior principal engineer. When he started in Intel in 1999 as a product development engineer, he worked on the first Intel P4 processors on thermal and power issues. Over the last 20 years, he's worked on the entire line of client processors and a few of the servers. He's developed several test methods for high volume manufacturing, as well as device validation. Arun has an MSEE degree from UARC with a focus on high density electronic packaging and thermal aspects of microelectronics. So it is a great pleasure to turn it over to Arun. We'll take questions interactively as he goes. Arun, all yours.
Hi. What are we talking today? So why it wouldn't move? Okay. So today we are going to, I'm going to introduce the generic problem what we have today, especially for the product development engineers. We are the people who actually help the ramp of the manufacturing of the products. We will have a unique view of what is the problem for tester vis-a-vis system, because all the time, we talk about system is good, but when it comes to tester, we have problems. We will see hotspots of the various dies, and I'll show some of the Intel dies, both one client and one server, and power density trends. And you just heard Gamal talking about power density, and we'll see that. What tests are we talking about? And typically the scan, array, and functional tests, which are in the high volume manufacturing. We look a little bit deep into the guts of these tests, why there is a power increase and where in the test and how their power is increasing. And we have some mitigations. These are not permanent solutions, and what future solutions we need to solve this problem. Okay. So having said that, this mouse, okay. When you are chasing the top speed or top bin for your product, no one is happy about the SHMU. And the SHMU is basically, frequency on the x-axis and voltage on the y-axis, and every point is basically a pass fail for thousands of tests, thousands of patterns, and you need a good green area on this corner. And I don't have that. And even this particular green spots are flaky. That means I don't have a 5 gig part to sell, and no one is happy about it, right? But guess what's going to happen? Some engineer is going to come up and then show me, hey, Arun, I ran this part 17 degrees lower temperature and see that full of green. That means we have a product. Now, that is the nightmare starting for a thermal guy like me, that, hey, product works, but I cannot test. And guess what? All hell breaks loose. The architects come and tell me, hey, I have architected this, product to run at the top speed. In fact, run 1 gig higher, it'll run. Design guys will come and say, hey, I have done PVT for this perfectly. Why is HMM having problem? My friends from validation, Murthy and RJ, will usually with 1 unit, they'll come and say, hey, I'm running okay on the system. What is your problem? The DFX guys who generate the test vectors and all those things and fabric and everything, will come and say, our DFX is good. Our tests are passing. In fact, you yourself are showing that tests are passing. Hey, run it at top speed. And our fab and assembly people will tell them, don't burn up my silicon, don't break my package. So it is your responsibility to make it. Our Q&R man gives no break for me, no relaxation in TJ, no relaxation in TDP, rightfully so. That is their actual job. They say, no, no, no. That's what the answer is from them. And of course, don't ask about planning. Planning will come and say, wait a minute, I need 15% top bin split next week, and don't increase the test time and clog the factories and crater my fab capacity. Thank you, solve this problem. And me, the product development engineer, starts yelling at people, it is too hard to test. And that is today's actually the whole seminar is about that, right? Let us take a little bit deeper view of tester versus system. I mean, you saw that the validation people are able to come and tell that, hey, my my system is functioning okay, and we cannot test it on the tester. The reason is this, that on the system, we have thermal management, throttling, and power management, and all those things, which keep the silicon intact at lower power or within the power envelope and keep the TJ, throttled and TJ raise in control. But in tester, we use all DFX kind of mode, which usually bypasses all thermal and control loops, internal thermal control loops. In fact, scan test will immediately kill all the thermal control loops, basically, because it's a test mode. Our test patterns are very short compared to the system, benchmark. System benchmarks can be long, and the thermal control feedback can kick in because you have enough time to see the temperature rise and control. But in tester, we go boom, 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 boom. We burst through it, very sharp transient, and TJ rises exponentially, in fact, meteoric, right? Cores, we have multi-cores, right? For test efficiency, we usually run them at lock steps. And this is called, the tester deterministic, curse of determinism. And we have power spikes, and all of them have the power spike exactly at the same cycle. But it doesn't happen on the system because cores and threads are almost asynchronous, and temporarily the power is distributed. And in order to test the maximize our core and IP testing, we run them together because economy is the king, and we end up having high power test in the tester. But in the case of system, the number of cores running is limited by the SKU or stock keeping unit configuration or architectural definition. Means if you're running turbo, you run one core, and if you're running 2-core turbo, you run 2-core. You don't run all the cores and all the EUs at the same time at the topmost frequency, right? Test power can be 2 to 10x of the spec power. Means the TDP of the part could be 60 watt or 35 watt, but on test, I can create a scan pattern which can easily go 3x or even 8x the power, right? And and we usually try to run things outside of the test, the specification envelope. And also on the temporary thermal interface, this is the problem because on the system, there is a robust thermal interface. You put the compliant or semi-permanent TIM, almost flat surfaces on the motherboard. There is no warpage, and we screw them properly and everything. But on the tester, since we are doing millions of units, it's a temporary thermal interface, usually dry, sometimes liquid, inconsistent because there's a million times you are socketing it, not always the best flatness you get, and warpage and all these things are bad. So we have a huge problem. It's a whammy. It's not even double whammy. It's 10 whammies on the tester. On the other hand, system guys are much better, right? This is the problem we face on the tester. So looking a little bit deep into the silicon itself, right? Both client products, which is laptop and desktop and the mobile parts, versus server parts, produce high power and high power density hotspots. You can see the pictograph there. The hotspots are on the cores, and the client on the left has got something like 4 cores and about 12 hotspots. On the other hand, a server with 18 cores will have more, right? Many hotspots, and they move around with workload. It's not like one position they are going to be. As we run the number of tests, these hotspots move around. I took a snapshot of one workload, but these move around, and you can see the small hotspots, they become big, on some other test. Gamal was telling earlier, there was, what happens to the corner effects or edge effects or crowding of the hotspots. All these problems happen. This is a silicon phenomenon, right? TIM1, TIM2 packaging aspects, warpage and all those things influence a huge thermal TJ rise. Thermal mass between bare die and lidded part introduce unique challenge. The bare die is low thermal mass. It's a fast TJ rise, too fast for the thermal handlers to respond, in fact. On the other hand, the lidded parts have a huge thermal mass, which is good, which actually has a very good thermal capacitance to reduce the transient. But the problem is the thermal control equipment, if it tries to cool, it is too sluggish too. So it is one way it is good, another way it is bad, right? Finally, the chip layout, floor plan, IP design greatly influences power distribution. Our power densities of the various working load to test along with the total power is the key here, okay? So let us look at the historical trend of the power densities and geometry here. I started somewhere here, 1999, Pentium 4, I think it's about 130 nanometer, but even before that, the process node is coming down. This is typical Moore's law and all the way up to 10 nanometer. And the power density is increasing slowly. And it shot up somewhere near, Pentium 4. This is where I joined as a thermal engineer. You can see there is a steep increase. And even those years where actually we kept the process node same, the power density kept on increasing. The reason is that we come up with new innovations and increase the single core, single thread frequencies. And as the frequency increases, so does the power. So hence the power density is going high. So it is not uncommon to see, 4 to 4.5, watts per square millimeter. It's not like the entire core will have that power density, but the hot spots within 2 or 3 square millimeter, we can easily dissipate about 10 to 12 watts. It's very, very dangerous here. And the trend is not going down, right? It's only going up.
So
coming back to test. Yeah.
Arun, I think you may touch upon this, but there's a question, if the handler can't respond fast enough, what can you do other than change the test programming? Is there anything?
Yeah, that's a very good question. Hold on to it. I'm coming there, right?
Okay.
So yeah, exactly. Wait for a few more slides, okay? Coming back to test. What tests are we worried about? We have array tests, scan test, functional test. These are the fundamental tests for any silicon manufacturer. We have IO test and analog calibration, but these IO tests and analog calibrations, they are static temperature sensitive tests. Means you test at 100, you test at 90. Yes, there is some variation. There is some defect modes you can see, leakage variation and all those things. But these are not the ones which are really going to kill your product. The ones which are very, very interesting are these ones. The array testing, M-based, repair redundancy, and we throw the kitchen sink on it. Stuck at and at speed scan test. Functional is cache load, or we get structural based functional testing, or even the system ported test. Means you go and find out on the system there is something failing. You take that snippet of the code, microcode, and port it over to the tester. These are the real killers, by the way, right? And all of these are TJ race sensitive because these are the speed binning tests. Basically, your Fmax and Vmin come out of these tests, and they are extremely sensitive to temperature. And finally, since both of them are depending on temperature, basically you have a dF by dV problem, or dF max by dt, or dV min by dt problem here, which I showed it in the SHMU. Definitely the temperature plays a big role. And what the test operations we are worried about is SOT, because even though SOT is at a wafer level, or any other one which can be very, very problematic. And burn-in and stress, even though these are important, but the speed at which we run is very, very low. That means we are toggling at very, very low speed. So it is, even though there is a problem, but we are not going to talk today. Final test, or we call it class test. This is post-packaging test, is very important. System level test, even though my friends in system level test will come and say, hey, we do have problem, but I said they are actually better in shape than actually class test. So we will concentrate on wafer test and final test and these 3 tests here, okay? So let us take first one, scan test. Scan test, both at speed test and stuck at test, have a huge problem of huge switching capacitance, or total power and power density. You can see in this particular graph, this is basically a power profile of multiple tests going on, and all of a sudden the temperature shoots up and to when the scan is running, and this can go into thermal runaway very easily, right? The problem is not during shift in, even though shift in the C-dyne is higher, but shift in, we shift in the scan chain with few hundred megahertz. So, CVF or CV square F, your F is very low. So, it is moderate power density, but total high power because many chains are going to be running here. In the same way, shift out is once again low speed, not a speed critical because you are only taking the information out. So as long as the fabric is running, everything is good. It is the capture which is going to kill you because this is 1 to 2 clock cycles and you're going to run at the top gigahertz, and it has got a huge droop and huge power density. So it's a high power density. And if you're not very particular about how much switching capacitance you are consuming on the number of flops or number of latches you are operating, you can kill the part, or you can actually get a pseudo Vmin or pseudo Fmax, which is totally counterintuitive to the real world. The C-dyne or the test power for scan could be 3 to 10x of real world application. So you are running TDP or you are running any of the benchmark, but your scan test could be consuming something like 8x or 9x unless you are not very particular about how many flops you are capturing it, okay? The next one comes array test. Oh, this is a nightmare actually. Some of the nightmare cases I have seen in 20 years. Well, most of the companies run some sort of BIST, built-in self-test, or MBIST or a PBIST, programmable BIST or something, and we throw the kitchen sink algorithm on this. Mostly we get a fire and forget BIST engine. This is really good for test time and all the algorithms, but very bad for thermal control because the fast increase in TJ and hotspots, we don't even know that the temperature is increasing because there is no way to monitor the power or even the temperature, and we easily hit the Fmax or frequency wall, and we burn up chip. This is not only at packaged final test, even at wafer test, you can see the wafer damage here, right? It just burns up all the probes. And one of my managers used to say, "Oh, you burnt up a wafer, okay, bad Arun, but it is one wafer, it's okay." I go and tell him, "No, it's not only the wafer, I burnt the probe card also." And if a probe card goes away, then it's easily $50 to $100,000, and not only that, a downtime for the line. So it is a very bad test. So array tests are notorious for burning the wafers here. The pattern lists are too long, means usually we put all the algorithms and then boom, we go through like that without even realizing the temperature increases have started. And the worst is on server parts because servers have huge caches, right? Very long test. So we need to be extremely careful. There have been attempts to do a low power MBIST parts, but many times they give a false Fmax or even DPM risk. So we need to be extremely cautious about low power modes of array test, and a lot of correlation is needed. And the worst part is it's almost impossible to do a pre-silicon BIST power consumption model to make sure how much we need to test and how much we need to space out. So, if I go and ask my designers, I say, I don't know, you find out post-silicon, that's what they say, right? So the test efficiency, test time versus Fmax and quality is a constant battle over here. Finally comes the functional pattern. This is the cache load pattern or structural based functional pattern or mission mode. These are must-have patterns because these finally determine the bin or the Fmax of the part or Vmin of the part. Usually there are several thousands of functional resets classed back to back. We run within, in burst. They are very small patterns. They are something like 0.5 milliseconds, half a milliseconds, but they really pack a punch. Each one of them is, it's a peak here. Localized power density. These ones, as I told, these ones are the real important ones. And their double whammy is they are super sensitive to temperature rise and super sensitive to local droop. Highly transient power spikes, actually very hard to control the temperature. Often, and in test, we always run all the cores in lockstep because that is easy to generate in test. And test engineers, they generate the test and they are clock cycle lockstep. So that compounds the problem. Let us go a little bit deep dive onto this functional test a little bit. So this is called, I call it the anatomy of pattern. So you can see a two part here. First part is the part goes through several resets: global reset, chip level reset, SOC level, fabric reset, several resets and several configuration. And these are all the PLLs are locking and everything. This is huge power, but low power density because the power is distributed all over the die. But this sets the baseline TJ, means the huge power is drawn, the temperature elevates, and then my hot spots come in riding on the top of the baseline. That is a problem. And this is where the individual pattern comes. These are high power density, the local cache load happens, then local IP reset happens, and then this is the execute. Even though the power consumed here looks like only 60%, but this is the power density, as I was telling, within 2 to 3 square millimeter of the hotspots, I could be dissipating 10 to 12 watts. And guess what? This is going to repeat 1,000 times and moving around the hotspot at different locations. So this is the anatomy of pattern, and this is where we need to concentrate, okay? So, and as you look at it, this is one of the functional pattern, and you can see within, I didn't put the x-axis here, this is about 800 patterns, and this is about half a second or 800 milliseconds. All the thermal sensors, or sorry, hotspots started within 10-degree difference, and within immediately, you can easily see about 30-degree, temperature difference between the hottest spot and the coldest spot. And it is extremely difficult to control, and unoptimized TJ control, it will just burn up the part in no time, actually, okay? So what can we do here? Do I have a question here?
Yeah, a few quick questions. I mean, it's particularly talking about burning up the wafer. I mean, people are asking, is it microseconds or does it take time and you just don't detect it till later? I mean, is it, what are the,
so it's not usually microsecond. Maybe the damage is being done at microsecond, but the tests are long. The test could be anywhere between 2 to 3 seconds because your cache patterns, especially array patterns. In fact, you can run cache patterns for 5 seconds, 8 seconds non-stop. And during that time, it is very difficult to monitor temperature. The only way to find out temperature that something is going wrong is after the damage is done, the thermal runaway and the tester says, I'm drawing too much power. So tester shuts down because too much power is being drawn by the time the wafer is burnt or by the time the probes are melted. So this is a huge problem on the wafer test.
Good. Okay, understood. And then a question, at least most of your figures look like monolithic pieces of silicon. Do chiplets make it easier or harder?
Actually, chiplets make things better, I would say, but it depends. Like if you have a smaller silicon, smaller chiplet, but once again, if you're going to go and you go crazy on your scan on that particular small silicon, even though that small silicon could be actually dissipating only 2 watts in real life, you can go and burn up 20 watts on that small silicon. You will have a popcorn instead of a small chip, right? And later you will find out that small chip is the one which is creating problem. It has happened to me before. Okay.
Yeah. Thank you.
So what can we do? Thermal equipment can alone not solve the problem because the thermal feedback alone is not sufficient. It is too late because inside the silicon, the temperature is rising within milliseconds or maybe in 10 milliseconds. And by the time thermal control equipment figures it out, it's too late, right? Heater following mode or thermal diode is very slow. Often there is only one thermal diode or maybe 2 thermal diodes, and they are far away from the hotspot, right? Baradai has problem because they lack thermal mass and we don't have a very good thermal interface material, right? So they heat up very fast, they basically. And the leader part have thermal mass because they have a nice hat on them, right? Integrated heat spreader. They smoothen out transients, actually. They push out the hot, what they in temporarily. But once the temperature is increasing, the thermal control equipment tries to act, but it's now counteracting the thermal equipment, right? So it is help and at the same time not good. So we need to address the source of the problem, the heat generation, reduce the power density, right? So what are the mitigations? Some mitigations here, these are not solutions, right? Core separation. For example, nowadays there are multi-core or multi-IPs or multi-EUs, right? Spread the heat temporarily in time. So this is actually I call this curse of determinism or curse of lockstep for test engineers, right? In this case, you can see we started with 4 core and we know the power is going to shoot up. So we separated 2 cores at a time. But this is not easy. There is no clean way in test pattern generation or test programs and everything which will easily do. Lot of hand holding, right? And the binning program and everything is very complicated. So this is not easy for a normal engineer to do. So we need to come up with some good way for these things to be easy. If they find that the top bin is having this problem, do this only for the top bin, because this is not test time economical, because you're going to, in the case of server, if there is 28 core and you have to do 2 core at a time or 4 core at a time, your test time explodes, right? So you need to make sure how to do this better. So we need to come up with some way. Or you can interleave narcoleptic or cooling patterns. In fact, I showed the SHMU before. Somebody reduced it with 17 degrees. Same effect can be achieved by putting cooling patterns between the patterns, right? But once again, it is not consistent because some patterns are hot, some patterns are not that much hot. How much cooling you will put, at last you will end up having 2 patterns and it is too conservative and test time is going through the roof, right? And such a pattern, if you make one pattern list, you use it for all the SKUs, which is totally counterintuitive. You don't want it, right? And many times we do this pattern reordering and test time reduction effort post silicon or post manufacturing and everything confuses heck of a lot, right? But this can be done. This is one of the solutions, sometimes we have adopted, right? Third one is forced cooling, or this is where the thermal control equipment can come into play, that you can temporarily step down the temperature momentarily and then go back when the speed binning happens or the top bin happens. This is very difficult. This is very confusing for the thermal equipment, actually. It suddenly goes cuckoo because all of a sudden, what is happening? You are loading a new recipe and then doing something. And even the DUT needs to be stopped because you are changing something in between. It has to be powered down and powered up, and a lot of confusion, actually. And I have even heard from the thermal control equipment, people don't do this, Arun. Actually, it actually spoils it screws up our thermal control equipment, MTBF. It may not be a very good HVM option, but it can be done, right? So this can give respite to some situations, right? Finally, on the scan patterns, we should be able to tune the scan pattern C9, how many flops how many latches you are catching. And then if you tune down this, you can see the temperature has come down considerably, right? For the same exact pattern, we can tune down it. Chopping down the chains, that is an easy way out, but it is counterproductive. Your yield analysis and everything goes screwy, right? Confuses the coverage, yield signature, and all those things. Thermal tuning only for scan is labor intensive, actually, right? And whenever there is a new revision of silicon, you have a new simulation and all those things happens. Once again, we need to go and redo this every time. So this is a very problematic effect too, by the way. Reducing power density at the foreplan stage is the best option, in my opinion, right? So what are we going to do in future, right? These are the solutions we want. And I want actually industry to step up and then give the design and architectures a power density and temperature aware IP design. Means at layout level itself. It's not like, oh, silicon is made and Arun is screaming and how to help him. I mean, it's a post facto. No, we want this to be pushed into the layout stage, and we want tools so that the IP design engineer says, okay, I put X square micrometer of white space near my hotspot, and every design manager will kill me to put a white space, which is no use. But if the design manager is capable of getting that ROI analysis right in the beginning, that if I put 10 square micron of white space, my TJ is going to go down by 4 degrees. Fmax goes up, Vmin goes down, power goes down, performance goes up. If that ROI analysis is available right at the beginning of floor plan or IP design, that would be great, actually, right? And DFX side, we need actually scan tools and all those things to come up with on the fly, on the tester, seamless change of C9 or activity factor for at speed test, right? Array and MBIST, we need low power mode, period, right? We definitely need it. We need simultaneous execution of many MBIST, but somehow we can make it low power without breaking the bank, without having quality. If we do it, then we need this basically, right? Easier tools for core separation or IP separation or staggering, because the test generators will come and give you a test which is almost lockstep. But can we have core separated out even during simulation, so that, or emulation, so that these need not be done post silicon, and then we scratch our head, hey, did we do that right, or is there a functional problem over there, right? Telemetry, of course, we need more DFX, on-die thermal management, which doesn't get killed in DFX mode. If it is there, it will be great. I think that is a great investment we can do. Of course, more sensors on SoC, you can spring, more thermal sensors all over the silicon, especially within the hotspot will be great. There is a research needed because area efficient, ultra small DTSS, if it can be peppered around the entire IP, especially third-party IPs, automatic plumbing, it will be very good, right? On the other hand, the tester thermal control equipment, we need better thermal control, very faster ones. In fact, if there is a way to monitor hotspot, it will be great. Thermal test program and the handler handshake, especially when we are doing the change of handler set point and feedback elements and how much cooling it's needed. All those tester to handler handshakes need to be brought up. Better TIM. If I can have a better TIM, even a test, it will be great. Higher thermal capacity, faster response. Today's thermal solutions are, in my opinion, much, much slower compared to the silicon temperature increase. And it is an age of data, so I think we need to come up with intelligent algorithm, intelligent data analysis, and put all those things back into the thermal control equipment. With that, let me take some questions if we have time.
Okay. Thank you, Arun. Some really quick questions. You've talked both about active thermal control on the handlers and also the chucks and the wafer probers. So what you talked about is applicable to both environments?
Tell me again, I couldn't hear.
Yeah, is what you talked about applicable both to package part handlers and
oh yeah, definitely,
probers?
because wafer probe is coming to be a problem actually. Both the server products and client products and even FPGAs in that respect, right? Because we need basically, even though we have a post packaging class test, best thing is to get a known good die at the wafer. So everybody wants to do all testing, especially multi-chip era, right? Even one chip faulty, that means you throw away every die on the package. So we want to test everything on the wafer probe. So temperature control at wafer probe is becoming a problem.
Right. And related to this, and I believe both Dave and Ken will talk about it a little bit more, but the question was asked, why can't the tester detect that the current flow is exceeding a certain limit to avoid burning of the probe?
Too slow, because the tester has got a big power supply which has got a ton of capacitance, and then it goes to the TIU or the test board, which has got tons of capacitance. And then you have a prober, and then prober has built-in capacitance. And then the silicon has got MIM caps most probably, right? And then finally comes your transistor. The transistor burns up faster, and the tester finds out after a year of electrical, time, hey, I'm drawing too much current. Right.
Wow. Okay, lots of great stuff here. More questions than we have time for, so I want to thank everybody for those.
Please contact me or send a question to Ira, and I'll try to answer.
Right, and I'll pass you the list of questions. So want to once again thank our sponsors who made this event not only possible, but made it free for everybody to attend: Advantest, Amcor, Indium, Form Factor, and Nidec SVTCL. And Advantest, once again, is a global leader in the ATE industry with nanotechnology products supporting leading edge with a diverse workforce and eco-friendly policies. Amcor is driven in the areas of technology, quality, and service in terms of advanced packaging, high quality execution, and a complete array of services from design and test through drop ship with a manufacturing footprint throughout the world. And Indium, with premier assembly materials designer and manufacturer, thermal interface materials, solders, paste fluxes, and materials and compounds. So when you have an opportunity, please thank all of our sponsors and encourage them to help drive future events, but we're very thankful for their support of Too Hot to Test. And I will wish everybody a good rest of your day. Thank you for joining us.